Today we're going to begin our discussion on chemical equilibrium. We've looked at it a little bit before when we were talking about liquid vapor systems in equilibrium, and I had that example of my water bottle out with the lid on it, and how you have some of those liquid particles escaping to the vapor phase while others are condensing down, and those things are happening at equal rates. And that's the thing that is important, and what I expect you to know at this point about equilibrium. Equilibrium involves reversible reactions. We know they are reversible by this double-headed arrow that's right here. And they tell us that the reactants will combine to form the products. And if this thing is in a closed container, meaning it has a lid on it, then the products can recombine to form the reactants. And that will happen at equal rates, not equal concentrations. And that's important to keep in mind. Now, equilibrium is a dynamic state. That means things are always changing. It is going back and forth between reactants and products. And that is happening at equal rates. Now this reaction here, I couldn't get my double-headed arrow to print out, so that's why I drew it in there. We have an acid here, and this happens to be a strong acid, which means that it does dissociate 100%, or really close to 100%. So you have this hydrogen bromide. The hydrogen disattaches from the bromide ion and attaches to the water molecule to form hydronium and your bromide ions. Now, if you'll notice, this arrow right here, the small one right here, this reverse reaction, it's a shorter arrow. Now that's a tiny, tiny little difference. But really what that's telling me is that the forward reaction is almost complete. It is almost completely dissociated before the reaction rate is high enough, the reverse reaction rate is high enough to establish equilibrium. So for the most part, this is a forward reaction, but there is a tiny, tiny little bit that does go in the reverse. But we do end up with more products than reactants. Now, this little symbol right here that I was talking about, this little half arrow that looks small, what's happening there, that's really just too small to even notice for most chemists and probably you as well. So we have another way to tell us which way the reaction is going to go, whether it is producing more products or more reactants, or about the same. And we do that by writing equilibrium expressions. Now this is going to be very similar and probably pretty easy since we just finished writing rate law expressions. There are some similarities there. All right, this is my Mach equation. Capital A, B, C, and D are all compounds or elements. N, M, X, and Y are your coefficients. The way you write every single equilibrium expression, and you'll have a lot of practice with this on your homework, is they start out, the constant is K, and it is a capital K this time, and it's products over reactants. Now that's always assuming a forward reaction. So if you look at a reaction like a forward reaction, it is products over reactants. So our products, C and D, are here. It is their concentration. That's why we do have the square brackets. Concentration in molarity of each of our products multiplied together raised to their coefficient power over the reactants A and B, again in square brackets, so it is their molarity, not moles, but molarity of these guys multiplied together, raised to their coefficient power. Now K is the equilibrium constant. It's sometimes written as KEQ. Also, sometimes it is written as KC. We'll try that again if I can write it on here. Writing an eraser. There we go. KC, because we're dealing with concentrations. All right. It is the equilibrium constant, and it is constant for this reaction at this temperature. If the temperature changes, K changes. But that's the only time K actually changes, is when temperature changes. So let's practice. I have this equation, the formation of hydrobromic acid, and we need to write the equilibrium expression for this one. So it is going to be K equals products over reactants raised to their coefficient power. So it's the concentration of my product, which is HBr, and its coefficient is 2, so it's raised to the second power, over the concentration of my reactants multiplied together. All right, now the subscripts don't go out there. It's only the coefficients that it's raised to. Okay. So we have a problem now. At equilibrium, a 2-liter vessel containing, now I can't see that, 0.36 moles of H2 and 0.11 moles of Br2 and 37 moles of HBr. What is the equilibrium constant for the above reaction at this temperature? Now, they generally will specify a temperature, not that you have to do anything with the temperature. It's just that it is constant for that reaction at that temperature, and so it is just specified. All right, so we're going to try and calculate K. The first thing we need to do is we need to figure out the molarity of HBr, H2, and Br2, because that's what the square brackets mean. They mean concentration in molarity. So first, let's talk about HBr. You take your 37 moles and divide it by your 2 liters, because that's the reaction vessel is a 2-liter reaction vessel, and we get 18.5 molar. H2 is 0.36 moles divided by 2 liters, so 0.18 molar. And bromine is 0.11 moles divided by 2 liters to give me 0.055 molar. Now, this is going to be a little more difficult than the problems I'm giving you for your homework. I'm going to go ahead and give you the molarity, but I do want to make the point that it is molarity and not moles. So don't put moles in this reaction or in this equation. So now I'm going to use this equilibrium expression, and now I just have to plug things in. Remember that HBr is squared, and the other two are not. So K, I have my equilibrium expression. Now I'm going to plug everything in. My 18.5 moles goes in for my HBr, 0.18 for my H2, and 0.055 for Br2. And then I just divide everything. We're going to say that K doesn't have units, and I know a lot of you will be happy for that. And so 3.5 times 10 to the 4th. Now that is a pretty large K value. What that is going to tell me, since it is a large number and K is always products over reactants, that means that we are forming more products than reactants. And so with our equilibrium, we are going to end up with more products than reactants. If K is a small number, and I'm talking times 10 to a negative number, all right, for the scientific notation, that means that we have more reactants than products. So the forward reaction is really hard to get going. And if it's in the middle between like 0.1 and 100, then it is a pretty equal split on which we have more of products or reactants. There is a little trick here with writing equilibrium expressions. A pure substance can be eliminated from the equilibrium expression. And you have to watch out for this, and you have to pay attention to the unit, or not to the units, but to the states of matter that things are in a reaction. If it is a pure solid, so it has a little S written beside it in parentheses, or a pure liquid, so a little cursive L there. Those things don't really have a concentration. It's hard to get a molarity because molarity is moles per liter. So we say that their concentration is 1, and basically they just drop out of the equilibrium expression, and you do not write them at all. They will also have no effect on that equilibrium position. So in this reaction that I have here, we have one thing that we can get rid of, can eliminate. We can get rid of carbon because it is a solid. It is not going to enter into our equilibrium expression. Now in your homework, you will have a lot. The first few are all gases, but then I get to some where I throw in some liquids and solids, so make sure that you pay attention. So if it's gases, or if it's an aqueous solution, so it has an AQ, those do go into the equilibrium expression, but pure solids and pure liquids do not. So my equilibrium expression here would be K equals products over reactants raised to the coefficient power. So my product is CO2, because it's on this side of the arrow, and my reactant is O2. I eliminated that solid. All right, that's all as far as we're going to go today. I'll pick up tomorrow with shifting equilibrium tomorrow.